So today I'm going to tell you a little bit about my latest work, some of my thesis work, and also some of the kind of work that I like to pursue in the next few years. So specifically, I will tell you about how to combine research from data mining, two areas, data mining and human-computer interaction, to help people make sense of large graph or large data set of graphs. So naturally, I work with large graph. So what is that? Right? Some people call it large network data. So what is that? Then here's some examples for you. So for the internet, you can consider it or view it as a large graph of 50 billion web pages. So each node in the graph would be a web page, and then a link or web link would be a link in the graph. And Facebook, so I need to keep updating this page. So now you can think of it as a 1 billion node graph where the node in the graph is a user, and then an edge would be a friendship, right? And you can, in academia, you can have these large graphs, constructed from a paper. So each node in the graph would be a paper, and then an edge would be a citation edge, right? So there are actually a lot more examples like that. You can construct a who follows whom graph from Twitter, Amazon. You can construct a who buys what graph. So each node will either be a person or product in the graph. And of course, like cell phone network, who calls whom. And in biology, you can figure out how protein and protein interact with each other. So there are many, many more examples. And these graphs are not only getting bigger, there are many more of them these days. And they provide us with new opportunities to understand a lot more things, like how people interact. If you look at the Twitter graph, you look at the Facebook graph, you can understand the people's purchasing behavior. You look at the Amazon graph, like what's the buying trend, and also help us prevent diseases. For example, if we know how proteins interact, then, well, we can develop new drugs, target-specific properties. So here's some of the example large graphs that I personally analyze. So notice that they are in the order of million or billion of nodes and edges at least. And the largest one is the second one. So the first one is what we call the Yahoo web graph. So it's a snapshot of the web. So each node would be a web page and a link would be a web link. So it's a little bit old, probably around 2002. So that's why you only have 1.4 billion nodes or web pages and 6 billion edges. And the second one, which is the largest, is a graph from Symantec, the company that develops Norton antivirus. And I will tell you a lot more about that in a few minutes. So in this graph, there are over 37 billion edges. So the node in this graph are either a machine or a file, and a file would, those two nodes will be linked together if the file appear on the machine. So that's a bipartite graph, we call it technically, because there are two types of nodes, and there are links between the two types, but not within the type. So having all these big data set, you will say, well, that's great, right? So a lot of opportunities, a lot of great things that you can do, but are there also challenges too? So if I ask you that question, the answer would be yes. And I would argue that a lot of the challenges come from due to one single number, number 7. So this might be a good audience to ask because a lot of you have HCI background. So anyone can tell you why that might be a challenge in dealing with big data sets. Yes?
Is it human memory, short-term memory capacity, but that's an overestimate.
Yes. This number keeps decreasing. So it's a very famous Millis Law. So it's basically, Miller found out that, well, on an average human, they probably only carry a very few, or process very few number of things at a time in the working memory. So 7 plus or minus 2. So for me, I think now it's maybe 3 or 4, something like that. So what that really means is that even if you have all these big amount of data, like billions and billions, trillions of records, what you really want to do is to help people distill the essence out of it. So in other words, you want to transform this big data set into insights, right? So it's really hard to do. So how do we do it? And what do we need? So this is what I want you to get some idea out of through my talk today. And my specific approach is to combine research from two areas, data mining and human-computer interaction, to take techniques from both areas, combine them to help people do that. And actually, each area individually, they have already been working for a long time on developing methods to help people make sense of data. But their approaches are very different. From the data mining side is focus on automatic methods, like summarization, clustering, classification, and so on. And these methods are quite scalable. So a lot of them naturally or very easily scales to millions or billions of nooks and edges. While from the HCI side, we look at the problem from a slightly different perspective. So we look at these user-driven iterative approaches, which take into account not only the task, but also the goals of the user. And some of the techniques generally fall into interaction, visualization, and so on. And these methods, because they are inherently like manual, human-driven, so they are less scalable, and they can scale to maybe thousands or tens of thousands of nooks and edges. So you may ask, well, two areas have long been working on that problem, so why do they need each other, right? So here is a simplified example. So suppose you're working at a cell phone company and your boss tells you that, hey, so we have all the data collected from our customer. So each node in the graph would be a customer, and then an edge would be a phone call. So you can build a graph out of it and say, well, so find out something of business value out of it. You have no idea what that means. What am I looking for? So one good way to start typically is to say, well, let's try visualizing data since we don't really know what we're looking for, do some exploratory kind of analysis. But if you try to visualize like a billion node graph, you would get something like this, very, very pretty. But then you don't really know where to go next. So if you can get some help from data mining algorithm, for example, you can say use an anomaly detection-based algorithm, then it can help you pick out something that probably are outliers or weird or things that you don't really expect from the graph. So, and you will, oh, great, so this could be my starting point, right? And some algorithms are even better. They will tell you, we'll rank all these anomalies for you. They'll give you a score. So the first one's most anomalous, second one's less so, and so on. So you give you a long list. And a lot of the algorithms, they will stop there, right there. They give you the list, they give you the scores, and that's it. They don't really, they tell you what, but then they don't really tell you why. So why are these highly ranked? So at this time, if you are able to use some of the techniques from the human-computer interaction, say I try to visualize the connection between the fourth. So I'm simplifying here because exactly determining what visualization techniques to use as a challenge. Suppose you can easily just visualize it, figure out an effective way, then you may see the first four actually form a clique. So the larger a clique in the network, the more suspicious it is. So in a cell phone network, what that means is you have this whole group of people who know each other. So not very typical. So through visualization, you can understand about that. And also, if you provide the right interaction technique for the user to expand on these nodes, they may find out that the last one, the fifth one, may actually correspond to the center of a star. So here, each node is a customer, right? So the center of a star could mean he's maybe a telemarketer, right? So he makes a lot of calls to different people, but those people don't know each other. So again, that's another type of anomaly. Then, well, only if there's right interaction tools, then you can find out about that. Yes, question?
So, Polo, do you think there's something that's inherent to HCI that would make it only scale to thousands of nodes? I don't really understand what. Is that just on average we tend to consider smaller graphs?
Right, so if you, no.
Why is the right solution HCI should consider a larger data?
So the goal, of course, everyone would do with as large data as possible. So, but there are techniques that were originally designed for scale, for small scale. So start with small scale that may not be able to scale to large data. So for example, just take a simple example of visualizing just all of that. It's not that you cannot do it, you probably can do it, but you probably don't want to do it. Right. So similarly for interaction too. So you may be able to interact with things, but then things might slow down, or you probably wouldn't be able to understand the whole range. So
you're saying that perceptually people do it better at thousands.
Yeah. So here what I'm proposing is to say, well, instead of relying on people to manually pick things out, maybe you can provide some computation support. So that's the key thing. So that's the kind of my main message is to say, well, so can we kind of take techniques from each side and then combine them so that they can help each other? So basically bridging the two areas and developing methods that can combine the best of both worlds. So this is a very quick overview of my talk to my PhD. And so I built out quite a few systems, and some in the data mining area, some in the human-computer interaction area, and some of them are intersection with them. So for this talk, I'll focus on 3 pieces of work. two in the data mining area and one in the intersection. So Polonium is a system that does malware detection over a 37 billion edge graph. NetProbe is another system that does fraud detection on eBay. So these two are purely data mining, but I will explain briefly that why these techniques would be useful for HCI. And the Apollo is a system for network exploring large network. So it uses machine learning in the background, which visualizing an interaction on the foreground. So combining these two to help people explore network. So these are the three systems that I will focus on. And specifically, I will divide these systems into three. I'll divide my talk into three groups and put Polonium and NetProbe into the first part of my talk, which I would call attention routing. So what does mean? What do I mean by that? So I'm hoping to show you that using these data mining techniques, we can help people to figure out what are the good starting point for them to start the analysis with. So essentially, you want to route people's attention through this whole big data to specific points in the data set. So route the attention to specific points. And then for the second part of my talk, I will argue that, well, just having these data mining algorithms is not enough because they make mistakes, right? So, and then also different people have different preference in what they want to look at. So it's useful to have users' feedback into the data mining process to guide the algorithm. So to the algorithm and the user work together. So I will talk about the Apollo system, which is a mixed initiative combining machine learning and visualization. And then in the end, I will talk about the kind of work that I find really excited that I like to work on, that I see also there's a lot more research these days on. So I think those are good direction in this area. So I'll start with the first system, Polonium. So it's published in the SDM 2011, top data mining conference. So to help you understand the contributions of Polonium, I'm going to quickly tell you what existing technology malware detection does. So it's based on what we call signature-based detection. So meaning the malware software company, say Symantec and McAfee, they would try to generate a signature for each piece of malware that they know of. And then they would distribute all these signatures to the user as updates. That's why you get a lot of updates from them. And then your computer would scan, your computer would scan for files that match those signatures. And well, there's a problem with that. So the signatures are created a lot of times are human. So that means if there's no signature generated in time, you cannot do the detection. So how do we have a more scalable way of generating this signature, or in more higher level, how do we determine whether a file is a good or bad without relying on a lot these signatures? So that's where the Symantec's new approach called reputation-based detection approach comes into play. So they're trying to compute what we call a reputation score for each application in the whole planet. So the idea is to say, well, if we can find our reputation of a file, then we can say whether it's good or bad. So low reputation, poor reputation means a malware. Good reputation is a good software. So I'll tell you in a second what that means by how to compute the reputation score. But suppose you do have that, then you could do this classification. And so Polonium is one example. Technology that's based on this reputation-based approach. So it computes a reputation score for each application, and it's now patented, not patent pending anymore. It's a work that I led as design and development as an intern several years ago, and they were really happy with the initial results, and they are now deployed. Polonium is now deployed in all the latest Norton antivirus software. And it has now served over 120 million users worldwide and answered over trillions of queries for reputation. And so that means if you're using the latest Norton antivirus software, you'll be using a piece of Polonium, or actually a piece of me, because I name it after myself. So it has Polo in it. Yes. So it's the best time to name a system after yourself when you're a grad student, because you create it. So, and it's just not my name, and it also describes how the technology works. So the full name for it is propagation of leverage of network influence unearths malware. So the key is network influence. So in a few slides down, you'll understand what it means. So it's the key concept that we use to kind of label these files into good or bad. So I'll start with a little bit about the data that Polonium works with. So a few years back, the data was about 60 terabytes, and it's collected from over 50 million machines that anonymously reported about their executable files. And there are over 900 million files total, each one uniquely identified by its cryptographic hash value. And the goal is very simple. We want to determine whether a file is good or bad, right? Good or malware. So you would ask, so this seems like a classic classification problem. So why is it hard? So there are three reasons for it. So the first reason is that now we're dealing with a much bigger data set. So that means algorithms, methods that work well for a small data set may not necessarily work for large data. So first one is size. Second one is here we wanted to detect all kinds of malware that Symantec is already flagging, not specific type. So that means if you have a technique that works really well for one type, it may not work well for others. So here we want a pretty general method that can detect all types of malware. And the third reason is that we want a false alarm rate to be really low. So false alarm meaning you mistakenly classifying a good file as bad. So say Microsoft Word.exe, if you classify it as bad, that's disastrous because they affect millions and millions of people in the world. So we want the false alarm rate to be really, really low. So for all these reasons, it becomes a tough problem. So how do we deal with it? So one way to think about it is to, well, treat every file as an individual record and ignoring all the other information which we thought was very useful. So what we did instead is we take into account the relationship between the files and the machines that those files appear on. So specifically, what we did is converting the data into a bipartite graph. So a node, say this node, if it's reported by two machines, then there will be an edge linking from this file to this machine and this file to this machine. So it becomes a bipartite graph, bipartite because there are two types of nodes, files and machines. And there's no edges between each type, but there are edges between the two types. And after this transformation, this graph has about 37 billion edges and 1 billion nodes. The nodes are either machines or files. And Symantec already know some information about the files. So they know some of them are good, some of them are bad. And the goal is still the same, right? We want to find out about the question mark file, so whether they're good or bad. Right, so that's a formal problem definition. So a little bit about the information that Symantec does have. So they know some files are good, some files are bad, so they call that known good and known bad files. And they put it in a ground truth database. So how we might use this known good and known bad information is we can say, well, for a file that we know is known good, then we can say its prior probability of being good, or a prior information without doing really anything is close to 1 or 0.9. So if we map it to probability value, then 0 would mean really bad, 1 is likely to be very good, 0.5 you can treat as unknown. So, and then there is some other things. So say they might have a rough idea about whether a machine is maybe careless or not. So say if a machine doesn't really run updates or get the latest update, then it's probably a careless machine. Then again, you can map this carelessness to, say, a score between 0 and 1. 0 means careless, 1 means careful. Right? So that means they do know a little bit about some file. They know a little bit about some machine, may not be accurate. But they do know a little bit about it. So the idea now is, so well, can we use all this known information about the files and machines and use it to somehow transfer that to the unknown file here? So how do we infer whether this is a good file or not? Right? And the key idea that we used is what we call guilt by association. So what that really means is that things that are similar are likely to be connected in the network. So that means if I'm guilty for something and if I know you, then you are probably also guilty. So you are guilty by association with me. So guilt by association. So how do we use it here? So in this case, what that just means is good files are likely to be connected to good machine, bad file likely to be found on bad machine. Right? So actually that's quite intuitive that if you think about it. And in many fields it's called homophily. And more technically, you can represent it as a 2 by 2 matrix. right? So the rows are file, good or bad, and machine are good or bad. So here, these are not the actual value that are used in the algorithm, but it gives you an idea. So it's a high value for the diagonal entry. So it's saying good file are very likely or have a strong strength of association with a good machine, low strength of association with bad machine. So that's the key idea that we use to kind of propagate the information. So how do we exactly do the propagation? So with that, there's an algorithm called belief propagation. It's a very powerful inference algorithm that's used in many domains. Yes?
For the previous
Yeah.
situations, we have an empirical evidence for that supports this.
Yeah, a short answer. So the question is there empirical support for this intuition-Gilbert association? So the short answer is yes. So the exact value is now learned from the real data that Symantec has. So that's why I say it's not like this, but is in similar kind of relevant degrees. Yeah.
How big is the coverage of ground truth data from Symantec?
So exact number I cannot tell you, but
But
it's in the tens of millions. So in that order. So I will have like one short sentence to talk about the size of the real data. Okay, so we use the Gilbert association concept, and we use adaptive belief propagation algorithm to do the actual propagation of known information to the unknown information. And it's an algorithm used in many domains, solving many of the hard problems. Actually, a lot of them are the state-of-the-art performance. So PPT is given the state-of-the-art performance, like in error correcting code. If you are familiar with that, one of the best error correcting code is based on belief propagation. So here we adapted to help with malware detection. So instead of going into the details about how the algorithm works, I'm going to give you a really short example of how it works on a toy graph. So you can think of this as a dramatically scaled down version of the Polonium graph, of 37 billion edge graph. Here we only have 4 files and 3 machines. And the goal here is to figure out the reputation of file 2 and file 3, which are currently 0.5. That means unknown. We don't know whether it's good or not. And we already know some information, as in the real case, that some files is good, like file 1 is good, file 4 is bad. So close to 1 is likely good, close to 0 is likely bad. And similarly, we have an estimate of the machine's current reputation, whether it's, this one is 0.6, so slightly good, 0.45 slightly bad, and then it's even worse, right? So how do we do the propagation? So the goal is here to figure out these 2 files' reputation from the rest, right? So belief propagation, there's a reason for it to be called belief propagation because it propagates things. So in the actual algorithm, we would propagate this known information. It can start from either side, from the machine or files. So here we say start from the machine. So what it does is that each machine would send a message to the file that is connected to. So basically to say, to tell the file what's its opinion about it. So for example, machine A, for this message, it will be telling file 2 that, hey, you are probably good because I'm good. Why is it so? Because we are using the homophily concept, right? The idea. So things that are similar would be connected. So that means machine A is slightly good, so it will be telling file 2 that, well, you are probably also good. Similarly, machine C would be telling file 3 that you're probably bad because I'm bad, right? So that is what each message is about. And then each file would then collect all the incoming messages, aggregate them, and to update its approximate reputation score. So that means file 2, this is the aggregated values, 0.58, so slightly better now than 0.5. So that's a current estimate. So it's by aggregating the 2 incoming messages, right? So that's one way of propagation. And as you imagine, it's an iterative process. So it would go the other way around. So once the file has an updated reputation, it would go back to update the machine's reputation, right? So similar idea, similar things. So now you have a better estimate of the machine reputation. So you keep iterating this until the algorithm converges, meaning until these values do not change anymore. So that's the theoretical thing, but I will quickly mention in a few slides that was a lot of the time we don't really need to do it to convergence. So in case you're really interested in the details of the algorithm, here are the all the equations that you need to know to implement this really scalable algorithm. There are only 2 equations. So instead of going through the symbol by symbol, I'm going to show you what they really mean intuitively. So by mapping it to the example that you already saw. So one equation tells you how to compute the belief or the reputation. So meaning if I want to compute the file reputation for file 3, what I really need is my incoming opinions, what my neighbor tells about me, and then also my prior belief, what I knew beforehand, even without doing anything. So you combine all these, actually the multiplication, and then you'll be able to get the estimate. So that's what you get for one equation. And then for the second equation, as you would expect, so it tells you how to compute an opinion. So this is the opinion for neighbor. So it's telling you that what you need is just your current estimate for your reputation, so this whole thing. And then you apply the transformation. Technically, it's called edge potential. So this is also the guild by association matrix that we saw previously. So that means if this is good, then the opinion would be a positive opinion sending to the neighbor. Right. So that means you know how to compute the opinion. You know how to aggregate compute opinions. Then you can compute the reputation score. So that's all the details. And so we evaluate this method on real data. That's about millions of ground truth data. So known good and known bad combined. And we use the standard tenfold cross-validation machine learning. So basically that means we divide the data into 10 parts using 9 parts to set the prior of training and using the remaining 1 part for testing. So this chart shows you how well Polonium does. So x-axis is false positive rate, meaning how many good files wrongly labeled as bad. So that means ideally we want it to be close to 0. We don't want any false alarm. Right? And then the y-axis is the true positive rate, how many good file correctly identify as, how many bad file correctly identify as bad. So that means we want all bad files to be correctly identified. So the ideal point will be up here. So Polonium does about 85% true positive rate and 1% false alarm rate. So you would say, well, 1% is still pretty high. That means 1 out of 100 is wrong. So here, this percentage is actually considering each application as only counted once. So meaning if, say, Microsoft Word.exe is counted as wrong, then in the real world, it would be affecting millions of people. But we don't really take into account that actual number. We only count it as 1. So we treat each application as a single separate entity. But we do take into account how many times that a file appear on this machine, then this number becomes significantly lower because most of the time the false alarm happens for the files that Symantec doesn't know that much about. So meaning, so if a file only appears on, say, 10 machines, well, not much you can do. It only appears on 10 machines, right? So that means in real world, 1% is actually 0.0000000 something. So it's really low. And then another thing is that after integrating this method into Symantec's existing frameworks, it's able to boost those existing methods by 10% absolute point in terms of performance. So meaning that's a very significant increase because imagine you have an existing technique that's doing 90% accuracy. Now it does 100% accuracy. So there's an absolute percentage increase. So it's a very significant increase. So after looking at how well it does, we also look at how well it scales with the data. So this experiment was done on a single machine, so not using clusters. So they are using clusters with many machines, so it's much faster. So even with just one machine running over 37 billion edges, it takes about 3 hours to do it. And it scales linearly in the number of edges in the graph. So it's pretty good. And a little bit details for those of you who are working with large data sets. So how do we actually make it work on 37 billion edge? So one trick we did is we do what we call early termination. So it's related to kind of iterative nature of the algorithm. So meaning we don't really need to run the algorithm through conversions because all we care in the end is whether it's good or bad. So as long as above a certain threshold and stay there, then it's good. We don't care that much about the exact value. So early termination, faster running time. Second thing is due to the nature of the algorithm, we don't really need random access to the edges. So that means we can keep all the edges on the graph on file. And we do sequential scan in each iteration. So hard disk is good, very good for sequential scan, bad for random access. Since we don't need random access, we can keep the edge on the graph, on disk. And the third thing is even more detailed level is that we can actually cut down the computation in half. So in the previous toy example you saw, I chose to start my propagation from machine and then file, machine, file, machine. There's actually another independent path that starts with file to machine, file, machine, file, machine. So there are actually two paths going on in each iteration that will eventually give you the same thing. So that means you can remove one part and make the computation twice as fast. And so with the experiment on single machine, then we also look at how well it would scale when we have multiple machines. So we had the Hadoop implementation of the propagation, and this chart shows the scale up, so comparing to the baseline of 25 machines. So it's roughly linear. So if any one of you have worked on these parallel systems, you would know that it's really hard to achieve true linear scalability. So anything close like this is really good. So for this experiment, we did it on the Yahoo M45 clusters, has about 500 machines. So that is Polonium. So how do we use it? How do analysts may imagine using it? So you can think of it as one way of routing people's attention or analysts' attention. So there might be certain files that are getting really, like bad files that get really popular, but maybe the analyst doesn't know about it yet. So those are potentially important things because that means that particular malware is spreading. Right? So if you can use Polonium to quickly identify those files, compute a reputation instead of relying on signature, then you can suggest those to analysts as their starting point of analysis. So that's one example. And then there's a second very quick example. It's another way for to help people identify what are the suspicious things in a network. Specifically in an online auction, such as eBay. So it's one of the very first data mining project that got me hooked onto data mining. So it's still a very exciting project, and because the problem is still very important. So here we're trying to find out who are the bad guys on eBay. So people who take your money and don't really give you the good. So who in the audience have used eBay? Okay, very good. So I should have asked the reverse, who have not. Anyway, so it's still an important problem. Auction fraud was the #3 online crime in 2010. I don't have the latest figure. And so how do we find the bad guys? So one way to think about it, or the way that I want to look at it, instead of treating these people as individual persons, look at it as a network of people. So each node in the network would be a buyer or seller, and edge would mean a transaction. So among this network, who are the bad guys? It's really hard to find out. So there's a lot of manual that can go into forums, like Ford Report and so on. And is able to figure out that, well, first of all, bad guys are really smart. So they would try to fabricate this reputation score on eBay. So for each user on eBay, you will have a little number that says how many positive reputation or how many positive feedback that the user has collected. So fraudsters are really good at fabricating this number. And the specific way that they did it is that they create two types of identities. One type we call the fraudster identity, and then the other type, the accomplice identity. So all these identities may or may not actually be controlled by the same real person. But these two types serve very different purposes. So the fraudsters are the identities who eventually trade with the victim or defraud the victim. And the accomplices are identities that act pretty much like honest people. So they would trade with honest people. If you just look at the transaction history, you probably can tell anything weird happening. But then occasionally, an accomplice would trade with a fraudster for some really expensive things, like LCD TV, laptop computer, all those super expensive things. So the reason they do it is they want to make this particular transaction look really trustworthy and carry a lot of heavy weight, right? Because if now you want to trade with this potential, this person, and you see that from his feedback history that is paid on time, he has paid on time for the really expensive items and so on, well, then you would think that this is a trustworthy person. So that is the way that we discover about how they would fabricate, the kind of the architecture that they use to fabricate these reputation. So what that also means is that detecting these kind of fraud becomes trying to identify this particular structure from the network. right? In particular, this structure is what we call a near bipartite core. So it's bipartite because we have two types of nodes. As a core because it's a graph in the whole graph of transaction. And it's near because there are actually some missing edges. For example, this one is not connected to all 5, but only to 4 of them. Right? So how do we detect it? So at that time, there was no known algorithm to do it. So we tried a whole bunch of algorithms. And in the end, we found that belief propagation worked out really well. So in this case, we are not only using homophily, but we're also using heterophily. So heterophily means similar things are actually not likely to be connected. So if you show it in like a 3x3 matrix, then that will be clear. So what that means is that fraudsters are not likely to connect to fraudster. It's likely to connect to accomplices. So more saturated means more likely. So this is for the heavyweight transaction that I briefly just talked about. So very likely to connect to accomplices. Not likely to connect to honest people until the very end when they're ready to defraud them. So similarly, accomplice likely to connect to fraudster, not likely to accomplices, likely to connect to honest people because they want to act like honest people. Similarly for honest people. So what that means is this 3x3 matrix is exactly describing this near bipartite core pattern that we want to detect. So this becomes the input to the algorithm. And then applying out real data with over 800,000 transactions over 66,000 users, we're able to spot these real confirmed fraudster. So the red nodes are the real confirmed fraudsters that we pull from news forums and so on. And what's even better is that we are able to find all the accomplices and then the other collaborating fraudsters. So these are real cases that we're able to find. And so this work we received quite a bit of publicity and attention, including eBay. So they invited me to the campus to give a talk, and also appear on these news outlets. And importantly, it got the attention of Symantec. So that's how they invited me to work on the Polonium project. So they thought, well, if you work for eBay, probably you work for us. So yes, they're right. So we work for them as well. Yes.
I'm just curious, so how did you figure out the edge potentials? Was that based on ground truth data and the eBay thing as well?
A little bit. So the question is, how do we figure out the 3x3 matrix thing? So we did not have enough data to really learn the whole matrix. So it's a little bit of intuition plus a little bit from the data, because the actual number of cases that we're able to find is under 100 known fraudsters. So we're not able to learn from just that. So it's a little bit intuition too. Yeah. Right. So, and then there's something I forgot to mention. So whenever you are trying to battle bad things, the bad guys will come to you. So they will try to contact you. In this case, they contact us as Belgian police. They'll say, hey, so we're really interested in your work. Can you send us your source code for, yeah. So of course, no. Yes. And, yeah. And so for Network, we also developed a user interface to help users understand what's happening. Yes.
Sorry, I'm just curious. So you said you didn't want to send them the source code, but it seems like your algorithm should actually be robust to things like that, right? It should be robust to gaming because you're using inherent behavior. Is that right?
So the question is like whether our algorithm is robust to behavior.
Would the algorithm break if you gave them the source code? I had a hunch it wouldn't. Right?
So I think other people were defrauded by the time it caught up. That's not good.
Yeah. So all these problems is typically arms race, right? So when you find out what the bad guys do, you have a detection method, then they would come up with a new thing probably. So they could actually read our paper and they figure out all the parameters, but they ask for the source code. So yeah, so there's good reason to ignore them. So they should read the paper, yes, and cite me, yes. Yeah, so we have the UI, and it's purely presentation. So meaning we only show the people what the algorithm has detected, and sometimes it makes mistakes, right? And there's no way for the user to correct a mistake or incorporate their feedback. So that brings me to the second part of my talk, exactly for the same reason that, well, algorithms are great. They can go through a lot of data very quickly, but they there are weaknesses, right? They don't incorporate user feedback easily. It's kind of like a one-shot approach. You run it and then you get your result. So in other words, it doesn't really have the user kind of explore what are the potential other patterns that they may want to look at, what are the things that we want to look at next. So the Apollo system is a system that kind of fill in this gap. So basically add the user into the data mining process and work with the algorithm to interactively explore a network. So Apollo is published at CHI 2011. CHI is a top human-computer interaction conference. And it combines machine learning and visualization to help people do the exploration. And specific problem that it tried to tackle is to help people find more relevant nodes in a network. So meaning if you're interested in a few nodes in the network, what are the other nodes that you might also be interested in looking at? So here's a concrete example, looking at a citation network. So each node would be a paper, and an edge would be a citation. So suppose, or imagine you are a grad student, a first-year grad student. Your advisor say, well, you are interested in HCI and data mining. So here's two papers to start reading. HCI paper, data mining paper. Okay, after reading it, go figure out what other paper you might want to read. So, yes, how would you do that? So intuitively, you would imagine papers that are close to your current interest will be what you are interested in. So close here meaning the papers that are citing your paper or being cited your paper. And actually that match a lot of the cases that what people are actually doing, right? So how would you find related paper? You either go to Google Scholar or maybe you will read this paper and see what this paper has cited. So that means you go to its neighbors, right? And similarly, when you're reading this paper, you may say, oh, what other paper may I want to look at? So look at related work, what has it cited? So you go to this. So that means papers that close or closely connected, like maybe through many paths or actually directly linked to your current interest might be more relevant. Further away, less so. So what that also means is actually we can use skill by association, right? And this case is a very different scenario, very different use. We're using it to explore data instead of doing classification, malware detection. So I'm going to show you a quick demo about how Apollo works. And specifically, this scenario is on helping the user or helping a grad student to understand or to map out the sense-making literature. So sense-making is a field in HCI. So it studies how people make sense of information. So as you would expect, it overlaps many research areas. So what we're showing here is kind of the outcome that we want to see after the whole scenario. So the user, or our imaginary user, would be starting with one paper that's called the cost structure of sense-making. Same information you can see here, down here, title, authors, and so on. So this data is citation data that's crawled from Google Scholar. So anything you can get from Google Scholar, you can find it here. So note is a paper, and edge with a citation is directed because you get direction in the citation. One paper citing the other, right? And the size, note size is the number of citation related with the number of citation that a paper has. Larger the size, more times it's cited. So in this data set, we have about 80,000 papers, crawled from Google, and 150,000 citations. And this is kind of what we want to get out of in the end. So in here, we identify there are three research areas: collaborative research, information management, and information visualization. And also, we're able to find out what are some good example papers, good key papers that are particularly relevant for the three areas. So this is the user interface of Apollo. In the beginning, when there's only one node, my starting paper, the cost structure of sense-making, we will show you on the right the papers that either directly cited it or linked to it or being cited by it. So on the right, when you click on it, we click on the paper, and they are sorted by citation count currently. So for this scenario, I'm cheating a little bit here because I already know what all those papers are about. So I'm glossing over like actually looking at the paper abstract and so on. So I'll just focus on the paper title. So my first thing I would do is I go to the list and I say, whoa, so are there any general area that I may be able to find just looking at the title? So there is. There's one pretty general thing called information visualization. And then there's another one. The title is called Search Together, so it's about search. So why not I create two groups or put them into two bins? One we call it search. And then the other, I call it, what do you call it? Info vis, right? So now I have two groups. So there's two things that happen. One is automatically assigning a color to them. And the second thing is these two papers actually become the exemplar papers of the two groups. So remember in the toy example that I showed you, so these two papers now become kind of source or your current node of interest, right? And by doing that, then you can use the algorithm to infer what other nodes are relevant to those two. So that's exactly what I'm going to do next. So since I have an example for the search group, then I can ask Apollo to add 10 other papers that it thinks are relevant. So color saturation here means relevant. So more saturated, more relevant. So it's already ordered by that. And quickly skimming through the title, I can see the first one is relevant, is about search. And the second one also is about search, co-search, collaborative search. So pretty good. And I think that's good enough for now. Very quickly, I already found some relevant papers to read. And then now I go back to my starting paper and say, oh, why don't I look at some papers that directly link to it? Right. And here, all the papers by default are sorted by citation count, so all the size of the paper. But since I have the two groups created, so I say, why don't I sort them by how likely the Apollo things belongs to InfoVis? So that can help you quickly identify relevant paper to InfoVis. So if I look at just the title, then I see the first one is about information visualization. And then the third and fourth, the second and third also. So now you actually see a pretty obvious change in the color saturation. So some of the papers become more saturated. So actually that's a good thing, because since color saturation mapped to the relevance that Apollo infer, so more saturated, now that means the algorithm also think these are more relevant to the search group. Yes, question?
One thing that I noticed being somewhat familiar with the discipline is that all of those 4 papers are by the same overlapping set of authors.
Yes.
And so given that, successful scientists tend to have it turns out it correlates well with certain self-citation strategies as well. So a confound in this if I want to find diverse papers as opposed to cliques of body of work by a successful group.
Right. So the question is like whether we can find diverse group diverse papers. So by construction, I think it would be pretty hard, like with the modification, because we're only based on the link structure. Right, so only on link citation. Right. Yes, but there are data mining and machine learning techniques which basically solve the problems to find a diverse group. How to find good enough recommendation, but not kind of homogeneous, too homogeneous. Yes. Yeah. Right. So then, if I keep doing this, and then I can probably find another new area. Personal information management, then I can do the same thing, right? I can create a new group and so on. And then find other relevant paper. So I would love to extend this more to support all those other operations that are very important. Yeah, but this is how it works. It's very simple. And the user specify exemplars, and then the algorithm helps the user find out what other things they might be interested in. So you may ask, so why do we use belief propagation but not other algorithms? There seem to be many other things that you might use. Yeah.
Before you move on, so sort of riffing on Jeff's question, this seems to find highly central nodes in the graph. When often what you care about, given a certain literature search for the kind of thing you're doing, is something that's explicitly relevant that you might have missed. Mm-hmm. I feel like that would be another really interesting space to look at. Like, given what I know, these near misses.
Yes.
Because those tend to be far less central. There may be recent work or outside of the citation graph that you
Yes, definitely. So finding out what you are missing is definitely very, very important area. So we have been looking at that. We don't have a paper yet, but if you know how to do it, then yeah, we should collaborate. Yes. Yeah, so as you mentioned, there are a lot of things that we can do, like if we're able to bring in like algorithm and also the interface. So the particular algorithm that we use is belief propagation. So you may ask why we use it, not other things. So one major reason is that it already support a lot of desirable sense-making features. So like how when people naturally interact with data, what do we want to do? So we found that they want, a lot of the time, based on literature or also observation too, that they will create multiple groups, which belief publication directly support, immediately support. Multiple examples for each group also immediately support. And then I did not show it here, but it actually also support negative examples, meaning if there are papers that you don't think belong a group or you don't think belong to any group, you can specify two. So positive and negative example. And also it's fast. So as you saw previously in the demo, that is running in the background in real time. And so we're first to use it for belief propagation. So we also look at how this algorithm compared to all the other algorithms that generally fall under what we call diffusion type of algorithm. Like in HCI, there's spreading activation. In data mining, there's random walk restart or personalized page rank. So we look at how these compare. And in our PKDD, a data mining conference paper, we look at how they compare exactly. And we found that belief propagation is very flexible, so it can capture a lot of things that other algorithms can do, like random walk restart, plus more. So not homophily, but also heterophily, and so on. So that's the reason we picked it. Yeah.
Do you have any experience with using belief propagation for large networks that are not bipartite?
So the question is, have you used belief propagation on other networks that are not bipartite? Yes.
In my experience, BEP has convergence problems when it comes to large dense graphs.
Yes. Yes. So the major thing is that belief propagation, there's no theoretical guarantee that it would converge. So yeah, so we haven't really solved that problem. So we did try that on different real world data, and they seem to work pretty well. Yeah.
And even worse, you can cut early convergence, but the worst problem is that you have this pendulum effect. You go one convergence, another one.
Right.
So if you cut early, you.
Yeah. So there are cases where people have found in applying it on real world data where when the value do not converge, it might actually fluctuate between two. So I think we are fortunate that maybe due to the nature of data, we haven't seen that. But yes, that it could happen. It could happen. So a quick recap of Polo's contribution. So the first thing is that it's actually a very intuitive way for people to work with the machine. So one of the Polo user actually commented on that. He's doing things that he would do anyways, and now there's this added benefit of getting these automatic suggestion, and while they're doing these categorization. And the second thing is that Polo helped each user generate a very personalized landscape of the graph. So meaning, even with the same citation network data, depending on the examples that you give to it, you are able to generate these different grouping and different suggestions. And that's very useful in many cases, because imagine you're writing two papers, you might be looking at the same set of related work, but you would probably write about them very differently. You organize them differently also. So meaning same data set, different interpretation, different suggestions. So Apollo started back in 2009, so again, you would know that I have my name in it, Apollo, with one L. So it's literally my baby that was born in 2009. And this is the very first interface that we had. So now I can say it's a terrible interface, because it's just one box for each group, and then the bolder things are the suggestions, and the rest are the bolder things are the examples, and the rest are suggestions. So it doesn't really tell the user anything about the connection between the items within a group or across groups. So this was disastrous. So they prompted us to add in the visualization component, the graph visualization component. So now people is able to understand the suggestion a lot better. And we also found observed something that's really interesting, is that people don't really use the list that much anymore. They only use it when they want to compare things. So it kind of prompts us to remove the list completely, so that we have more space for people to work on the visualization. And we added the rank in place feature, which you saw, where we dynamically change the ordering of the items right in the visualization, so that when they need it, then they can do it. But otherwise, they can focus on the graph. So we did a user study to evaluate Polo. The data that the participant used is a citation network, which you already saw. And the task for the participant is to find related work for two sections of a survey paper that we gave them. So this is the actual paper that we gave them. It's called Past, Present, and Future of User Interface Software Tools. So it's a survey all these different areas of UI design tools, software tools. And so we picked 2 sections out of it, and then these are the 2 specific sections. One is called model-based generation of user interface. The other is rapid prototyping tools. So model-based generation meaning, can you automatically generate a user interface based on a model that computer scientists can create? So, and then you automatically, boom, get that UI. So there are a lot of research on that. And then the second area section is what are the tools that can help people quickly build user interface. So these are 2 sections that we gave the participants. And the task for them is to find related work for each of them, basically to update this paper. This was published in around 1990, so we asked them to say, well, find new papers that are published in the next 10 years. So it was a between subject study, so meaning we have 2 conditions, and each participant only use 1 software to do the same task. So there are 12 participants, and 6 in each condition using a Polo or Google Scholar. So they are grad students or research staff who have computer science background, but they don't know that much about user interface research. So these are the 2 sections we gave them, right? So each of them, for each section, they will find out the related paper. So we're pulling all together all these papers. We gave these papers to 2 expert judges who are professors. Actually, 2 of the 3 authors of that paper to rate those papers that the participant has found. So they will give a score of 1 if it's relevant, 0 it's not relevant. So each paper has a maximum score of 2 and minimum score of 0. So this is a result. So in short, Apollo wins. So Apollo is better. And for the model-based case, is only slightly better. The reason is model-based is a very specific thing. Model-based generation of UI is very specific things, and people can just type model-based in Google Scholar, and then they automatically find a lot of relevant paper. While for the prototyping case, it's a different story because prototyping is a very general concept that appear in many domains, like design, in engineering, and so on. So in this case, Apollo does a lot better, and on average, it's also statistically significant. So recap, yes?
So it wasn't statistically significant for model-based?
No, it's not. Because it's already very easy for Google Scholar. This one, for Google Scholar.
Well, I don't know, it seems to me like this is that your Apollo works really well when you don't have keywords, and Google Scholar works really well when you do have keywords.
Yes, you can think of it that way, yeah.
Okay.
So that says that for one search, you got no difference, and for another search, your Apollo is better.
Yeah.
So, right, I think we need more convincing.
Mm-hmm. More convincing.
Yeah,
So
it's
I think
only
that
working in one search.
it's actually more than one search, right? Because the user can do whatever they want with Google Scholar.
But they're searching for one thing, one target.
Well, we don't really know the target that they're looking for. We only ask them to find relevant papers. So anything they think are relevant. So that means they're actually they're searching for different things. They don't even know what they're going to find. We don't know what they're going to find either. So the argument that I would make is that for this link-based approach that Polo is doing, it's good to go from the one paper to the other. They're kind of directly linked, like through the network. We think that's better than just using keyword search because we actually know how things are kind of grouped or like in proximity to each other. So that's why we think that that's better than Google Scholar. So that also means you're doing a more local kind of search. Yeah.
So again, my response would be you did 2 searches on half of them.
Yeah.
Well, you got an effect and the other half you didn't.
Yeah.
It feels like it would be nice to substantiate it more.
Yeah, so we did have like a discussion and things like that in the paper. So yes, and I would be happy to talk to you more about that. Yeah, thank you. Yeah, so the quick recap for Polo. Yes.
How did he choose which edges to highlight and which ones to hide? Because that seems to make a big difference here.
Which edges to
Sure.
Like these?
Yeah.
Dark. So here when this is the edges that are directly connected to what I've selected. So it's just a visual artifact. It's not doing anything.
Okay.
Yeah. Yeah. Question?
Do you have any data on the relative speeds of the two systems, or like were people faster in Apollo than in Google Scholar?
Yes, I do. I think it's in the paper to look at like what's the average time that people spend on completing. So in the study we do cap the time that they spend on the whole task. I think they're given 20 minutes to find all these papers. Yeah. Okay, so now Polo is contributing to several projects, including the DARPA ADAMS project. So ADAMS stands for Anomaly Detection at Multiple Scales. So the goal of the project is try to detect these insider threats. So you may remember a few years back there was a shooter in a military base where a psychiatrist turned violent into a shooter. And so that's kind of the insider threat that DARPA is trying to flag. So they just say, well, can we detect who are the previously good person suddenly turn bad? And for this project, Polo is now contributing as a major visualization component to help the analysts better understand what's detected. So that's Polo. So the second one, combining machine learning and visualization to help people explore a large graph. So the final part is about kind of vision or the things that I'm excited about, the line of research that I think are really exciting. And so big data, as you know, it's not the future because we are already there. So it's happening right now. And we're having all these large amount of data that are overwhelming many domains. And I believe that combining data mining and human computer action is a very viable way of approaching this challenge. And specifically, if we can create this new class of hybrid tools that combine the best of both worlds, then we can really take the expertise and intuition of people and also scalability of machines to deal with the challenge. So here are some of the example things that I'd like to work on. There are three things I'd like to focus on. The first thing is what I call enabling interactive data analytics. So one challenge that you might see when you're working on these large-scale data mining machine learning algorithms, so people will tell you that we have really scalable techniques, but they don't really tell you that you still need to wait for hours or even days to get your result, to work on it. Right, so wouldn't it be nice if we were able to look at even just a computation result from a subset of the data and then let the user to tell the algorithm that, hey, so what you've shown me so far, there's a huge chunk that I don't really care about. There's a little bit that I really do care about. So focus the remaining computation on that part. Then it can dramatically speed things up, right? So that's one thing, kind of the high-level ideas that I want to pursue. And specifically, we already started on that to using a really scalable algorithm in the back end that does graph mining or mining of a large graph, and then using Apollo as the front end for people to interact with the data or the subset of the data, and then give feedback to the algorithm. So for this package, the package is Graph Mining Package 1, then Silver Award in the Open Source World Challenge in 2011, and the whole work is submitted as a Signal demo in 2012. And the second area is, of course, to go beyond just graph data to many more data types, applications, and domains. So here's one example work that I'm working on right now is to develop an interactive visualization to help people understand results from topic models. So documents, we have a large document collection. The documents here are represented as the orange dot, and then the topics that are inferred from these documents are the blue rectangle or the blue squares. So how close a document is to a topic is basically the strength or how likely that the document belong to that topic. So by allowing users to move these topics around, they can actually do these ad hoc classification. So say you group like some topics in one and then the other topics in two. So immediately you get this line for classification. Actually, things that are close to those two, then they are more likely to belong to those two. So allowing people to play with these interactive visualization that can actually help them build a model about the data. And the third thing is what I call the collaborative big data analysis. So the work that I've shown you today, that, as you may notice, they actually what I call single-person analytics. So they're designed for basically one person. It's not really combining expertise from multiple people. And as you imagine, when we deal with these real-world complex data, you need more than one person to work on the analysis. And these people may be co-located, they may be distributed, different location. They may even be using different devices. Some may be using desktop, one might be using a tablet, or maybe even a phone, if they're doing like some kind of monitor job of the cloud. So how do we combine the input from all these different people, or maybe say two people working on the same problem, but they have a different mental map or landscape that they created from the data? How do we combine all these things? So that's a very exciting area that I think can really use a lot more research into. And so those are the three things that I'm interested in: interactive big data analytics, more application domains, and also the collaborative aspect. And with that, I'd like to stop here for today. And of course, I'd like to thank my host, Jeff, and also many of you who come here, and also my collaborators, industry, government, and CMU and Georgia Tech. So thank you very much.
Time for a few questions. Anyone has some?
So I'm curious about the collaborative thing for big data. So if you think about now, what will be the current most interesting work that has been done?
So collaborative.
Yeah.
What was the most exciting one that has not been done? So I'm very new to this area, so I don't know whether it has or has not been done.
I wrote my thesis on it.
Did you do any tablet work?
That was before the iPad.
My thesis was also in this area.
So I'm not
about 35 years ago in this department before this building was built, and it dealt with medical applications too, trying to extract information from a large patient databases. I'm guessing that's probably a huge potential application for that, where the nodes, where each node might be a patient record. Yeah, I'm trying to find similar patients and disease codes, or just letting the data speak for themselves to try and identify diseases.
Yes, definitely.
Huge.
Yeah, so healthcare domain, that's a big thing these days. And I think one challenge I would say is when you combine expertise from actually different domains, knowledge from different domains. I mean, not just talking about like all data mining analysts, but actually domain expert from like a healthcare or like actually medical doctors, and with the domain expert in data mining, all these things. So they have very different view even with the same data. They see things differently. So how do you combine that? I think that's a super challenging but very important area. I don't think that's enough work done in that area. So that could answer part of your question, and you should always talk to Jeff and for more. Yeah. Yes, Michael?
So I wrote my thesis on something else. But one thing I like about your work is that it finds a way to take some fairly complex concepts and make them scrutable in the user interface in a way that machine learning and interactive machine learning often struggles to make this interpretable. I'm wondering if there was some underlying heuristic or approach that you use in your work or moving forward that we could apply that you think would be profitable in that kind of direction.
Yes, so that's actually a kind of line of research I like to pursue, is to identify other classes of machine learning and data mining algorithms that are more amenable to being used in interactive applications. And what are they? And what are their characteristics? Because there are certain kind of algorithms that are really hard, kind of like black boxes, where you don't really know how to map or they may not even have parameters. But if they do, they might be very hard to map to like a user interface or how to surface it. In the Apollo work, we're mapping propagation to actually interaction. So user, when they put something in a group, you're actually changing the underlying probability or prior probability of the. So there are definitely like certain kind of algorithms that are more easy to work with, more easy to surface things, and I don't think there's enough work to in that area yet, but it's very, very important. I think people are starting to look at it. In terms of heuristics, I think based on, there's a PKDD paper that I briefly mentioned, we can start with all these different algorithms and try to identify what are the key commonality among all those, and we basically start from those. And picking out the right algorithm is often very hard. So I don't have like a magic formula to say, oh, so always try this first or always try that first. So you do need to understand a little bit about the algorithm and your problem. Yeah.
Let's thank our speaker.